If you go back just a few decades, these devices were a standard fixture on industrial buildings and farms. Even on residential rooftops across the United States and Australia, they were everywhere as an essential standard. But today, if you walk through any new housing development, you will struggle to find a single one. They are called turbine ventilators, or nicknamed Whirlybirds for their unique spinning motion. Independent tests have proven they can reduce peak attic temperatures by as much as 37 degrees Fahrenheit. This helps cut cooling costs by nearly 15% without consuming a single watt of electricity. This device requires no wiring, no circuit boards, and absolutely no electronic components. So if they were so great, why did we stop using them in modern construction? And if the test data is real, should we be bringing them back to our rooftops today? The idea of moving air through a building without burning fuel is one of humanity's oldest engineering solutions. We saw ancient Persian architects doing this with incredible ingenuity and precision. Tall masonry wind catchers called bedgears were designed to funnel desert breezes into the structure. They pushed cool air to lower levels while pulling hot, stale air out through the top of the tower. But the Persians were not the only ones who knew how to harness the power of moving air. During the Tang Dynasty, Buddhist monks integrated natural ventilation ducts throughout their cave complexes. This system helped control temperature and air quality deep underground for long periods. By the Middle Ages in Europe, air was regarded as one of the 4 essential elements of life. The way a building breathed was treated as seriously as the breathing of the people living inside it. These were all passive systems, relying entirely on the building's shape and wind direction. The shift toward more active systems began during the heat of the Industrial Revolution. Deep mines needed a way to keep workers alive underground in toxic and stagnant environments. Engineers responded with fire-driven ventilation systems and manually powered wooden fans. By the 18th century, the Houses of Parliament in London installed a primitive mechanical system called a blowing wheel. It was designed to replace foul, polluted air with fresh air from the outside environment. In the 19th century, David Boswell Reed built steam-driven systems specifically for hospitals. There, the risk of airborne disease made air circulation a matter of life and death for patients. But all of these systems required constant fuel, heavy infrastructure, and continuous maintenance. The real breakthrough came in 1910 thanks to an engineer named Samuel Ewart. He patented a design for a spinning cowl that sat directly on top of a roof ridge. It had the ability to actively pull air out of the space below it in a continuous cycle. Ewart's original patent describes the device as a solution for both ventilation and preventing chimney downdrafts. Those are the gusts of wind that could blow dangerous smoke back into a home. And unlike anything that came before it, his device required no fuel and no human input. Ewart's creation was simple yet extremely clever, drawing on 3 separate physical principles. To understand why it works, look at the common problem every house suffers from during the summer. Solar radiation heats the roof surface and turns the attic into a massive thermal reservoir. Temperatures inside that space can climb past 150 degrees Fahrenheit during peak summer days. This heat doesn't stay still. It radiates downward through the ceiling and into the living space. It forces your air conditioning system to run longer, work harder, and consume much more electricity. According to the U.S. Department of Energy, every degree of attic increase can boost cooling loads by 4%. In many homes, the AC ductwork runs directly through this superheated attic space. This means the cooled air is being warmed back up before it even reaches the intended rooms. The entire point of attic ventilation is to break this destructive thermal cycle. We need to move the hot air out before it has a chance to radiate down through the ceiling. That is exactly what Ewart's turbine was designed to do automatically and efficiently. The first principle applied here is Bernoulli's principle of fluid dynamics. As wind passes across the curved vanes of the turbine head, the air is forced to accelerate. When air velocity increases, its pressure drops significantly according to physical laws. This creates a zone of low pressure inside the turbine, generating a powerful suction effect. It actively drags warm air upward from the attic and exhausts it to the outside. The key point here is that the turbine ventilator uses the kinetic energy of the wind to actively drag air out. The faster the wind blows, the harder the turbine spins and the stronger the suction becomes. But here is what most people don't realize about this clever mechanical mechanism. The turbine does not stop working even when the wind dies down to a complete standstill. It fully leverages a second principle called the stack effect, or thermal buoyancy. This is the natural tendency of warm air to move upward through a confined space. Warm air is lighter and less dense than the cooler air surrounding it at lower levels. In a building with soffit vents at the eaves and a turbine at the highest ridge point, that rising warm air creates a gentle but continuous pressure gradient within the structure. It pushes air up and out through the turbine, even when the unit isn't physically spinning. The third principle involved in this cooling process is the famous Venturi effect. As air is squeezed through the narrow gaps between the spinning vanes of the turbine head, its velocity increases sharply at those specific restriction points according to physics. This increase in velocity further reduces the pressure inside the turbine housing once more. All three of these physical effects compound and amplify one another in a perfect cycle. The result is a device that generates continuous negative pressure at the highest point of the building. It constantly pulls hot, humid, and stale air out of your living environment. Simultaneously, it draws in cooler air from below to replace what has been exhausted. This simple design has been proven to be remarkably effective through hard scientific data. A study by the Air Infiltration and Ventilation Center provided very specific evidence. Installing a turbine increased attic ventilation rates by an average of 15% over a full year. Performance can improve by up to 50% when the wind hits the unit from its optimal direction. Data collected in the San Diego area showed that a properly installed turbine system works wonders. It could reduce peak attic temperatures by as much as 37 degrees Fahrenheit on hot days. This temperature drop translated to an average energy bill reduction of exactly 14.6%. To put this in practical terms, look at a standard 12-inch turbine unit's specifications. It can move between 250 and 350 cubic feet of air per minute at just 5 miles per hour of wind. A larger 14-inch unit pushes that capacity to between 350 and 500 cubic feet per minute. Because this device consumes zero electricity, every dollar of cooling savings is pure profit. Proper ventilation also prevents the overheating of roof shingles and structural materials. It stops moisture from being trapped in the roof deck, extending the building's lifespan for years. But these impressive numbers always come with an extremely important and heavy caveat. This is part of the reason why turbine ventilators are becoming rarer in modern suburban landscapes. A study from Deakin University found a significant physical limitation that users must consider. While a 12-inch turbine achieved a flow of 150 cubic feet per minute, the internal velocity was low. The resulting air velocity inside the roof space was only about 1/3 of a foot per second. In technical ventilation terms, this state is still classified as stagnant or still air. Their conclusion was that a single turbine is often not enough for modern thermal loads. This is where proper sizing and professional calculation become critical for any installation. Most building codes recommend 1 square foot of ventilation for every 300 square feet of floor space. But in hot and humid climates like Florida, many professionals recommend doubling that ratio. And the performance limitations are only one small piece of this complex technical story. The most problematic issue for the average homeowner was consistent mechanical failure. The defining feature, its spinning head, is also its primary and most common point of failure. Over time, the internal ball bearings can degrade due to moisture, dust, and lack of lubrication. They begin to produce a high-pitched squeaking or grinding noise that is very intrusive. This sound transmits through the roof structure and vibrates into the living space below. Cheaply manufactured units are especially prone to this rapid mechanical degradation. Over the years, this has given the turbine a reputation as noisy and unreliable hardware. But there is a more subtle engineering problem called the short-circuiting of airflow. Short-circuiting occurs when a turbine and a ridge vent are installed on the same roof above an attic. Because the turbine pulls air more aggressively and actively, it seeks the path of least resistance. Instead of drawing cool air from the soffit vents at the bottom to travel through the entire space, the turbine begins to pull outside air directly from the ridge vent located right next to it. This causes the air to only circulate in a small loop at the very top of the roof structure. It inadvertently turns a vent meant for exhausting air into an intake point for outside air. As a result, during severe weather, rain and snow can be sucked directly into the attic space. This is a total disaster for the wooden structure and the insulation layers of any modern home. For this specific reason, roofing professionals always recommend sticking to a single exhaust system. And in this technical showdown, the turbine is usually the first system to be eliminated due to complexity. But beyond these engineering factors, the biggest barrier remains the issue of external appearance. Turbine ventilators are highly visible and often look out of place on modern residential silhouettes. In today's housing market, curb appeal or visual aesthetics drive a significant portion of home value. Modern ridge vents feature a low-profile design that is nearly invisible under the shingle layers. They create a clean, continuous line that matches the sleek architecture of modern suburban homes. In contrast, spinning metal spheres tend to remind people of old, gritty industrial warehouses. Because of this, homeowners associations, HOAs, across the country have implemented strict bans. Many associations have prohibited turbines entirely, claiming they disrupt the uniform look of the neighborhood. They demand that every house maintains a consistent and minimalist appearance according to new trends. Even in states that protect energy-saving devices like Florida, HOAs still find ways to bypass the law. They often require homeowners to place turbines only on the rear slope of the roof, hidden from the street. But the wind does not care about human regulations or the aesthetic preferences of a neighborhood committee. Placing a turbine away from the prevailing wind direction can reduce its efficiency to nearly zero. This creates a negative feedback loop that makes these devices increasingly unpopular with builders. New building codes are also gradually shifting toward controlled mechanical ventilation systems. Standards like California's Title 24 require absolute precision regarding air exchange rates per hour. Since a passive turbine's performance depends entirely on variable wind speed and outdoor temperature, it falls into a regulatory gray area because no engineer can guarantee or control the wind. Contractors prefer systems where they can measure and commit to specific performance numbers on paper. An electric fan can guarantee exactly how many cubic meters of air are moved regardless of the weather. While it consumes electricity, it provides legal and technical peace of mind for the construction company. The rise of modern airtight homes has also been a major blow to passive turbine technology. In these high-performance homes, mechanical ventilation systems manage the entire air exchange cycle. Adding a passive exhaust point can disrupt the delicate pressure balance maintained by the HVAC system. However, the real question is whether we are collectively wasting a powerful source of free energy. For those living in hot and consistently windy climates, the answer is a definitive yes. In coastal regions or the American Southwest, the turbine remains an incredibly economical cooling solution. The material cost for a standard 12-inch turbine unit ranges from only $20 to $100. Professional installation might add another $100 to $300 depending on the roof's complexity. For a standard 1,500 square foot attic space, just 2 units are generally sufficient for the task. In southern climates, the energy savings can pay back the entire installation cost in just 3 to 5 years. It is a very smart investment if you aren't overly concerned about noise or suburban aesthetics. But in cold climates, the turbine can bring more unnecessary trouble than actual cooling benefits. During winter, internal moisture from the home can freeze directly onto the turbine's metal vanes. This ice layer can jam the system completely at the very moment when ventilation is needed most. When the turbine stops spinning, it loses the active suction provided by Bernoulli and Venturi effects. At that point, it becomes nothing more than a simple hole in the roof, less effective than a static vent. The truth is that for most homeowners building new today, a ridge vent is the more practical choice. A full-length ridge vent provides over double the ventilation area of 3 large 14-inch turbines. Because the ventilation is distributed evenly along the ridge, it eliminates thermal dead zones in the corners. While the traditional turbine is slowly retreating, a promising new rival has emerged on the scene. These are solar-powered ventilation fans, more commonly known in the industry as solar fans. This device directly addresses the turbine's biggest weakness, its total dependence on the wind. A small solar panel installed on top provides the necessary energy for an internal electric motor. It operates most powerfully at the exact moment when the attic space is hottest during the day. Unlike a turbine that spins slowly with the breeze, solar fans actively push air out continuously. They do not create that annoying metallic squeak because they use brushless DC electric motors. In terms of aesthetics, they feature a much lower and sleeker profile than the old Whirlybird. However, the price to be paid for this modern convenience is a significantly higher initial investment. A single solar-powered fan can cost 3 to 5 times more than a standard mechanical turbine. Additionally, the long-term durability of solar panels and circuits under harsh sun remains a question. While a metal turbine can last for decades, electronic components often fail much sooner in heat. This reality has led to a new trend in green architecture known as hybrid ventilation systems. This is a sophisticated blend of traditional passive design and modern active control technology. Engineers are returning to study how ancient buildings managed to cool themselves so naturally. They realize that relying solely on heavy air conditioning is an unsustainable path for energy consumption. Modern design thinking has begun to emphasize the creation of lungs for every new structure, utilizing internal atriums and light wells to generate a powerful, natural stack effect. In these designs, devices like turbines or solar fans only play a supporting role when needed. This shift is also driven by the new generation of architectural education and curriculum. Students are taught fluid dynamics and how wind patterns interact with specific building shapes. Instead of just mounting a device on a roof, they turn the entire roof into a thermal radiator. Some new roof designs use layered materials with air gaps to let heat escape on its own. This effectively replicates how the Buddhist monk caves from the Tang Dynasty functioned centuries ago. We are witnessing a fascinating reunion between ancient wisdom and high-performance modern materials. Even though turbine ventilators are disappearing from luxury and uniform suburban developments, they still maintain a very strong and dominant position in industrial factories and warehouses. In places where roof areas are massive, the electricity cost for exhaust fans is a staggering figure. In these scenarios, hundreds of turbines spinning continuously is an irreplaceable economic solution. They work silently, durably, and never demand a single cent of electricity from the owner. Their disappearance from residential rooftops reflects a deep shift in human priorities and values. We are increasingly willing to trade raw efficiency for aesthetics and controllable comfort. But in the context of rising global energy prices, many people are starting to ask the opposite question. Is removing a purely physical device to replace it with complex machinery actually a step backward? Many homeowners in Australia have started reinstalling these spheres after their electricity bills spiked. They are willing to accept a small amount of noise in exchange for natural airflow in their homes. Modern bearing technology has also been significantly improved to operate much more quietly. Sealed ceramic bearings are resistant to dust and water, effectively doubling the unit's lifespan. The revival of the turbine might not be loud or flashy, but it is happening very quietly. Manufacturers have also begun changing designs to make them look more refined and modern. Instead of shiny silver, they now come in dark tones to blend with gray or black roof shingles. The battle between efficiency and aesthetics has not yet reached its final or definitive conclusion. Every construction project is a balance between initial cost, function, and architectural beauty. But there is one undeniable truth throughout the 100-year history of the spinning turbine. Physics remains the most honest and sustainable solution that humanity has ever discovered. It requires no software updates, no grid maintenance, and it can never truly become obsolete. Those spinning spheres are a testament to the wisdom of the previous generation of engineers. They knew how to borrow the power of the wind to serve human life in a humble way. Understanding their mechanism helps us have a fairer view of these valuable old technologies. We do not have to choose between classic or modern, but rather find the most suitable solution. To understand why such an effective technology was pushed to the sidelines, we must follow the money. The global air conditioning industry is a massive market worth hundreds of billions of dollars annually. Profit comes not just from selling hardware, but also from long-term maintenance and replacement parts. A $50 turbine vent can operate for 20 years without requiring any additional costs. This does not create a sustainable or lucrative revenue model for large multinational corporations. In contrast, a central HVAC system requires complex installation and professional annual inspections. There is an implicit truth that building standards are often heavily influenced by powerful interest groups. When codes become overly strict regarding airtightness, they inadvertently eliminate natural solutions. They promote the idea that only modern machinery can truly control indoor air quality. But in reality, keeping air circulating naturally is the best way to protect a home structure. We are entering a new era where construction materials themselves can actively cool down. Scientists are developing radiative cooling paints based on the principle of emitting heat into space. This paint can reflect up to 98% of sunlight and push thermal energy out beyond our atmosphere. When combined with ventilation turbines, cooling efficiency will reach unprecedented levels. Imagine a building that requires no air conditioning, even during the most sweltering summer days. This is not science fiction. It is the optimization of what nature has already provided us. Future smart cities will no longer be scorching concrete urban heat islands. Instead, architecture will be designed so that the wind can weave through every single corner. IoT sensors will control shutters and turbine vents based on real-time local weather data. When the wind picks up, the system will fully expand intake vents to harness natural kinetic energy. When the air is stagnant or too cold, smart valves will automatically close to retain heat. This is the perfect intersection between the simplicity of the past and the precision of the future. But to achieve that vision, we must change our fundamental mindset regarding comfort and aesthetics. We must accept that a living house is a house that knows how to breathe. The absolute silence of a sealed room is sometimes actually a sign of a dead, stagnant space. The steady spinning of a turbine on a roof should be seen as the heartbeat of life within. It reminds us that humans are still in sync with the natural energy flows of the earth. In developing nations, where electricity costs are a massive financial burden for many citizens, reviving and repopularizing turbine ventilators is a deeply humanitarian and practical strategy. It helps poor families reduce the harshness of the weather without increasing their household debt. Municipal governments need policies that encourage these devices instead of banning them for beauty. Architects need to be more creative to turn these devices into a core part of their design language. A ventilation sphere can be stylized into a functional piece of art atop a modern structure. The social stigma against low-tech or budget solutions needs to be completely dismantled. We cannot solve modern environmental problems simply by consuming more and more energy. The lesson from Samuel Ewart in 1910 remains entirely valid for us today in the 21st century. Simplicity always carries within it the hidden power of longevity, stability, and resilience. When you see a spinning sphere on the roof of an old warehouse by the side of the road, do not think of it as an obsolete piece of junk about to be discarded by the passage of time. See it as a perfect physical engine working tirelessly and selflessly for human comfort. It is a reminder of an era when engineering was born to last and serve for generations, rather than modern devices with planned obsolescence programmed to fail early and often. Throughout the 39 minutes of this documentary, we have traveled from the past to the future. We have witnessed the rise, the forgetting, and now the potential return of a technical legend. Every rotation of that turbine is a silent affirmation of the correctness of natural laws. No matter how much the world changes, the wind still blows, and hot air will always seek to rise. Our job is to learn how to flow with those laws instead of trying to fight against them. Cooling our homes is not just a technical challenge. It is a challenge of human perception. And perhaps the best air conditioner in the world is the very atmosphere we are breathing. If only we know how to invite it into our homes in the most intelligent and respectful way. We often confuse the complexity of machinery with the genuine progress of civilization. But in engineering, the peak of sophistication is often found in extreme simplification. Samuel Ewart didn't invent the wind. He simply found a way to make the wind work for us. Over a century later, that fundamental principle hasn't changed even a single bit. As we face a global energy crisis, these lessons become more valuable than ever before. Every kilowatt of electricity saved through natural ventilation is a step toward true sustainability. It is not just about reducing your family's monthly electricity bill. It is about easing the pressure on the entire national grid and the global environment. A house is not just a collection of lifeless brick walls and cold roof shingles. It is a living organism that needs to breathe and exchange energy with the outside world. Enclosing ourselves in airtight boxes is a biological and architectural mistake. Learn to open the door for the wind and let the heat find its own way out via physics. In the future, we will likely see even more advanced versions of this spinning sphere. They might be integrated with smart sensors or made from new ultra-lightweight materials, but the soul of the device will always remain the movement of air through pressure differences. It is the invisible bond between the vast, open sky and our small human living spaces. When you build or renovate your home, take a minute to look up at your roof ridge. Do not see it merely as a shield against rain or a simple aesthetic component. See it as an opportunity to apply brilliant engineering knowledge that was almost forgotten. Perhaps your neighbors will wonder about the spinning sphere looking out of place on your roof. But when they see your electricity bills drop and your indoor air remain constantly fresh, they will understand that you chose wisdom over fleeting and shallow aesthetic trends. The journey of the turbine ventilator is a long story of the resilience of human knowledge. It has survived 2 world wars and a series of digital technological revolutions. It has quietly watched the rise and decline of cities from the highest points on the roof. Even if forgotten for a short period, it is always ready to serve humanity once again. Because the wind will never stop blowing, and the sun will never stop shining on us. And humans will always need a cool, fresh, and comfortable space to call home. Thank you for joining us throughout these 39 minutes of decoding this technical mystery. Learn to appreciate what is simple, for those are often the most essential things in life. The return of natural solutions is a testament to the maturity of our collective awareness. We do not need to fight against nature to achieve comfort in our modern lives. See you again in the next episodes about independent knowledge and sustainable solutions. Never forget to look up at the roof and listen to the whisper of the wind. It is the voice of nature trying to help us live better and much more intelligently. Every rotation of the turbine is a reminder of the harmony between humans and the earth. The world is changing fast, but the fundamental laws of physics will always stand firm. Let your house breathe, let it live, and let it be in sync with the atmospheric flow. The choice is in your hands between a power-hungry machine or a free spinning sphere. I hope you find the most optimal and sustainable cooling solution for your own home. The secret of the Whirlybird is now in your hands to use as you see fit. Our journey of decoding ends right here.